Hi, today we're going to talk about the relationship between free energy and equilibrium. So we're going to start with a relationship between the free energy of a system and the free energy at standard state. So up until now, we've been talking about the standard free energy change and how you can calculate that from values you can get in a table of thermodynamic properties. But what we're going to do is we're going to amend that now by adding this term that includes the gas constant, R. And since we're talking about energies, that's always going to be 8.314 joules per mole Kelvin. R times the temperature in Kelvin times the natural log of the reaction quotient. And if we add that term to the standard free energy change, what we're going to get is the free energy change for our particular system. Why would we need to amend the standard free energy change from the table with this term? Well, standard conditions include a number of different things. The conditions we usually talk about are 25 Celsius, that's probably the number one thing we say, 1 bar of pressure, some people say 1 atmosphere, they're super close, but also, if you're in a solution, 1 molar concentration. So if you think about this, your reactants are not necessarily going to be at standard state. And so that's why we have this general equation that can be true with any partial pressures or concentrations of our reactants and products. So what we're going to do is we're going to try this out on a reaction we've seen before, but we're going to look at it under 3 sets of conditions. So in this first condition here, we have 1 atmosphere of our reactant and less than 1 atmosphere of our 2 products. And our temperature is 300 Kelvin. So let's go ahead and plug this into the formula that we just looked at. The first thing we have to do is we have to figure out what our Q is. And let's just write the mass action expression that will help us determine what Q is. So our Q is going to be the partial pressure of carbon monoxide times the partial pressure of water. Those are our 2 products, so they go on top, divided by the partial pressure of our reactant, which is formic acid gas. So now that we have that expression for Q, we can go ahead and make it part of the regular formula. And then we're going to plug in all the numbers that we're given. So we have our delta G naught value. So that's the delta G under standard conditions being 4.4 kilojoules per mole. We have our value of R, our temperature, and then our concentrations of the various reactants and product. If you look, once again, we have our old standard disconnect where we have our delta G naught value in kilojoules per mole, and we have our R value in joules per mole Kelvin. So I have rewritten that here, and basically what I've done is I've calculated that whole second term, and I put our delta G naught value in terms of joules per mole. Now we have the same units, we can add them together, and we get a delta G value of negative 10,700 joules per mole, or negative 10.7 kilojoules per mole. So if you look at this, this is very clearly a spontaneous reaction. Now we're going to calculate the delta G when we have different conditions. Now, if you look at the partial pressures here, we have the partial pressure of our reactant is now 0.2 atmospheres, and the partial pressure of our products are now much larger, 4 atmospheres and 2.5 atmospheres. We still have the same temperature. So let's see what happens if we plug that into our formula. So here again is the formula that we came up with earlier that includes our expression for Q. Let's plug in those numbers, and you can see that we get a completely different value for that second adjustment term. And that gives us a delta G value for this system of 5,357 joules per mole. Let's just call that 5.4 kilojoules per mole. All right, we're going to look at one last condition. You'll notice that we have the exact same partial pressures as we did before. The only difference here is now our temperature is 500 Kelvin instead of 300 Kelvin. So same as part B, except with a higher temperature. So let's go ahead and plug in our numbers, simplify that second term, and we get a value of 11,862 joules per mole, 11.8 kilojoules per mole. So now let's compare these systems. With a delta G naught value of negative 4.4 kilojoules per mole, the forward reaction as written should be spontaneous under standard conditions. So if we had 1 atmosphere of everything. And as you can see in part A, when we had hardly any products, it was still spontaneous. So the system still wanted to produce a lot of products. But when we had high partial pressures of products, that shifted the system, and now suddenly the reverse reaction is spontaneous. That's what a positive delta G value means. And so what that means is we have too many products and we're going to form more reactants. And you can see that as we turn up the temperature, we get an even more positive value for delta G, which implies that we would be turning even more products into reactants. And so when you look at these conditions, you say, hey, this must be related to equilibrium and the sorts of partial pressures we expect at equilibrium under given conditions. So let's think about what would happen to this equation when we're at equilibrium. First of all, when we're at equilibrium, our delta G value is going to be 0. That was something we talked about in the introductory video about free energy. The other thing that's going to be true at equilibrium is that our Q value, our reaction quotient, will be equal to the equilibrium constant. So if you plug in K for Q and you plug in 0 for delta G, you can rearrange that equation and get that the delta G under standard conditions equals negative RT times the natural log of the equilibrium constant. So now we have a relationship between our delta G value and our equilibrium constant. Sometimes you're trying to find the equilibrium constant from delta G values. In fact, for me, that's more likely to be the case. So we can rearrange that to be the equilibrium constant equals e to the minus delta G naught over RT. And this is great because you can't always find the equilibrium constant you need at the temperature you need for your particular system. But if you have your thermodynamic tables, you can always calculate it. So we've talked about the equilibrium constant and how when it's a small number, that means that the system favors the reactants. Well, what does that mean in terms of what's happening in your system? It means products are turning into reactants. And so the reverse reaction is what's favored. And therefore, the delta G naught will be a positive value. By contrast, if you have a really large number for your equilibrium constant, that means that your system favors your products. You're turning reactants into products. Well, that's just the forward reaction, and therefore you will end up with a negative value for delta G. And you can see how that relates to our equations here. When you have a negative value for delta G, then negative times your negative value of delta G is going to give you a positive number. You're going to have e to a positive number. You're going to end up with a large value of K. But if you have a positive number for delta G, you're multiplying by the negative. So now you're going to have a negative value for negative delta G naught over RT. So you have e to a negative value. You're going to get a small value for your equilibrium constant. So now what we're going to do is we're going to look at two different systems that illustrate what I just showed you on that last slide. So our first system, we have two ammonia gas combining with carbon dioxide to make a solid and liquid water. So let's calculate the value of K, and we're going to use this equation here to turn our delta G naught value into an equilibrium constant. So let's first calculate what goes in that exponent there. Delta G naught over RT is going to be negative 6.53 kilojoules per mole divided by our R value of 8.314 joules per mole Kelvin times the temperature of 298.15 Kelvin. And you'll notice that we have our classic thermodynamic issue of kilojoules divided by joules. So I have switched it into joules. Again, you can do it either way. I tend to do it based on which math is going to be easier for that particular problem, but it doesn't really matter which way you convert. And this gives us a delta G naught over RT value of negative 2.634. Now we're going to plug it into our expression for the equilibrium constant. K is going to be e to the minus negative 2.634. So that's e to the 2.634. And so that will give us a K value of 13.93. Again, you can see this favors the products. So the forward reaction is favored, and that is what the delta G naught value told us as well. Here's another reaction, carbon dioxide reacting with hydrogen gas to form carbon monoxide and water. Our delta G naught value is 27.6 kilojoules per mole. So let's use that same equation. Let's plug our values into our delta G naught divided by RT expression, convert the kilojoules to joules, and so our exponent, we're going to have 11.13. So let's plug that into the equation for the equilibrium constant. We have e to the minus 11.13, and that gives us a pretty small number of 1.47 times 10 to the minus fifth. So now we can compare the two. We see our reaction in part A with a negative delta G naught value that favors the forward reaction, and that gives us an equilibrium constant that clearly favors the products. And in part B, we have a delta G naught value that's positive that tells us our reverse reaction is spontaneous. And that gives us an equilibrium constant value that shows that reactants are favored. When we were talking about equilibrium, I hinted that the equilibrium constant was not constant if the temperature changed. So now the question is, how does the equilibrium constant change with temperature? So we know that delta G naught is equal to negative RT times the natural log of K. And what I'm going to do here is I'm going to plug in delta H minus T delta S for delta G, because that is how delta G is defined. And so that equals negative RT times the natural log of K. Now, if we divide both sides by RT, what we get is this. Delta H naught over RT minus delta S naught divided by R equals the natural log of K. Before rearranging, we had temperature on both sides of the equation. Now that we've done that, we only have temperature in one place, and now we have a relationship between the equilibrium constant and the temperature. As we have done with other things in the past, we can turn this relationship into a two-point form. So if you know the equilibrium constant at one temperature, you can also find it at any other temperature. And that two-point form looks like this. And so this is going to work exactly like the Clausius-Clapeyron equation, the Arrhenius equation, etc. The differences are as follows. First, we have a ratio of equilibrium constants rather than a ratio of pressures or rate constants. We're multiplying our inverse temperatures by a ratio of delta H naught for a reaction divided by the gas constant. So that is also very similar to what we've seen before. So once again, when we're trying to figure out whether a reaction is spontaneous or not, we might know what it is under standard conditions, but a system may not be at standard conditions. And so whether or not a system is spontaneous does not just depend on things like the enthalpies of formation, it also depends on where the system is relative to equilibrium. I hope this was helpful, and I will see you again soon.